No matter where we are at any time of the day, we're always surrounded by waves. And no, not those kinds of waves. But we do experience waves related to the water. Those nasty UV waves. I know. But I wanted to go to Maine, relax, and eat lobster. Not become one. Yeah, you and me both, buddy. UV waves are just one part of the electromagnetic spectrum, along with radio waves, microwaves, visible light, and a few more. But these are only waves that affect electromagnetic fields, as the name suggests. Could there possibly be waves that don't fall into the spectrum? The answer presents itself in the discovery of gravitational waves. These are waves that actually affect the geometry of space itself. To begin to understand how gravitational waves work, we need to first know what space-time is. Space-time, also like the name suggests, is the combination of both space and time. Sounds pretty simple, right? I mean, we go about our day moving through space as time progresses. Seems like a logical train of thought, except space-time exists in the fourth dimension. One-dimensional time combines with a three-dimensional space to create a fourth-dimensional mess. But before you start to panic, it's okay, because our minds can't perceive any more than three. So, is there any way we can try to visualize this idea? By cutting down the dimensions to that within our comprehensible range, to say, the second or third dimensions, we can start to understand how time and space relate to each other. First, we'll need some supplies. To start off, we'll draw a squiggly line on a piece of paper. This will be our object space-time. Next, we'll cut a slit in another longer piece of paper. This will represent the present. We will slide the piece of paper with the slit over the paper with the squiggle to reveal an object in motion. As time moves forward, the present reveals that the object is moving through space as well. If we were almighty beings, then we'd be able to see something like the squiggly line where we can visualize and understand all points an object has been, at all points in time, for every object. Now that we're done with that, at least we're closer to understanding the relationship between space and time. And I thought my relationships were complicated. Because this would be way too much information to process, let's visualize the universe in Einstein's eyes according to his theory of general relativity, which makes space-time a smooth fabric that's distorted by massive objects. Other objects then follow these curvatures of space in a phenomenon called gravity. This leads us to our second experiment. For this, we'll have a flexible surface stretched over a pretty sturdy frame. Anything similar to spandex will work. This represents the fabric of space-time. Let's see what happens when we roll a ball across the fabric. It continues until it rolls off our space-time. Next, we'll add some weight onto the middle of our spandex sheet. Happy Halloween, by the way. This will represent a mass in space like a planet. Now, what happens when we repeat the same motion when the ball rolled off? Although the ball is going in the same direction as when there was no weight, it looks as if the ball is circling our weight. The ball isn't changing, but it is feeling the change of space-time. Now let's add two objects both of incredible mass that devour everything near it, like my stomach. Except, we'll be using black holes instead. Let's have the black holes orbit each other. Now the black holes are already giving off gravitational waves due to their natural acceleration, like a boat leaving ripples in the water. Energy for gravitational waves also comes from their orbital energy, the thing that keeps the objects from colliding, which will slowly be chipped away over eons until they eventually merge. But even though these are from something as massive as black holes, we still can't detect them accurately. However, when they merge, they release a huge amount of mass that's redistributed in gravitational wave form. This much energy was enough to distort the detectors in the Laser Interferometer Gravitational Wave Observatory to confirm the wave's existence. We experience waves all the time. We even feel the stretching of space through gravitational waves. These waves add new meaning to the phrase, "everything is never as it seems." So, maybe I'm not actually 5'2".